Welcome to Pomodoro Joe for Saturday, August 12th, 2023. Today we're doing LeetCode problem 63, Unique Paths 2. This is a medium problem. You are given an m by n integer array, grid. There is a robot initially located at the top left corner, i.e. grid 0, 0, right here. The robot tries to move to the bottom right corner, i.e. grid at m-1, n-1, all right? The robot can only move either down or right at any point in time. So it can only move down or we can move right. An obstacle and a space are marked as a 1 or a 0 respectively in grid. A path that the robot takes cannot include any square that is an obstacle. Return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9th. All right, so this seems pretty straightforward. This is a standard grid traversal, but we have some limitations. We can only move to the right or we can move down. So that actually makes this a lot easier than a standard grid traversal. All right, so let's put 25 minutes on the Pomodoro timer and we will get started. All right, you probably know what I'm going to say now. We're going to do a recursive solution. So if we had a function that tells us how many ways there are to get to a given coordinate or square, so if we had some x and y, we pass that into a function and it returns back the number of ways to get to that square. Then all we'd have to do is call it on this square here to get our result. Now, how does that function work? Well, there are only two ways that we can reach this square, at least two ways immediately to reach the square. We can come to that square from the square above by moving down, or we can reach the square by moving to the right from the square immediately to this square's left. So we can either move down this way or we can move this way. So the total number of ways there are to get to this square is just the sum of the total number of ways there are to get to the square above, plus the total number of ways there are to get to this square immediately to the left. So we can make a recursive function that, given this coordinate, will just recurse on the square above and the square to the left, sum those values, and that gives us the value for this square. So let's do that. So we'll have unique paths with obstacles recurse. And for this, we'll take an x and a y coordinate. All right. So normally I would do the base cases first, but let's move on to the recursive cases and then we'll come back to the base cases. So what are our recursive cases? Well, we just talked about this. If we could find the number of ways there are to get to the square above us, and the number of ways there are to get to the square to our left, then we sum those together to get the answer for this square. So let's have two recursive calls, one on the square above and one on the square to our left. So I'll do up, and that's going to be equal to unique paths with obstacles recurse. And for this, we need to pass in the square above us. So that's going to be actually x and y minus 1. So in this example, our coordinate system is like a screen-based coordinate system, where 0, 0 is the upper left, and y increases as you move down, and x increases as you move to the right. So because y increases as we go down, it's going to decrease as we go up. So if we go up, we go to x and y minus 1. And if we go to our left, well, that's just going to be x minus 1 and y. All right, and then we can just return up plus left. So that's our recursive case. Very straightforward. Now we do need to have a base case, otherwise this will keep going forever. What's the base case? Well, we're starting at this far right bottom corner, and we're going to be decreasing x and decreasing y. So basically when we get to 0, 0, or if we go below 0 on either one of these, then we're out of bounds. So let's make sure we stay in bounds. So the first check, are we at 0, 0? If we're at 0, 0, well then we're at the start and we return 1. So if x is equal to 0 and y is equal to 0, we're at the start and we can return 1. That's where we're starting. There's one way to get there. We start there. All right. Now we check to see if we are out of bounds in either the up direction or the left direction. So now if x is less than 0, we're out of bounds, so we can't get to that point, so we return 0. Now if y is less than 0, again we're out of bounds, so we return 0. Now we could actually combine these. If x is less than 0 or y is less than 0, return 0. Maybe we'll do that and see if it makes a difference in terms of optimizing. All right, and finally out here, we do need to call this for the first time. So we will return our recursive function, and we'll start at, let's see, we want to reach the end. We want to know how many paths there are to reach this last square. So let's actually have some helper variables out here. We'll have the maximum x. Well, that's going to be the length of our obstacle grid. Oh, I already see something I've done wrong. We haven't accounted for obstacles. We'll go do that in a second. So we have the length of our obstacle grid, and this is going to be row 0, and subtract 1 because this will be the length, and we're looking for the maximum index. All right, so we look at our first row, find its length, and that's how many x coordinates there are. That's how many columns there are. All right, and then max y, that's going to be the length of our obstacle grid minus 1. So that's basically how many rows are there, and that's going to give us our y. And of course we subtract 1 to get the index. Now here, we do want to start this off by finding what is the value at the max x and max y. So we'll do max x and max y. Okay, there's a couple things that we've done wrong so far. One is we're not accounting for these obstacles. I guess that is the one thing we're doing wrong. We're not accounting for this obstacle. Now, if we have an obstacle, what do? We didn't account for that here. Well, if there's an obstacle, there's no way to get to that square. So we'll check our obstacle grid here. If that is a 1, meaning there's an obstacle there, then we'll have to return 0. There's no way to reach this square. Okay, so let's see. I think one thing we didn't check, actually I'll check right now. Can we have an obstacle on the first square? Obstacle is 0 or 1. It looks like we can. So it's certainly possible that we have an obstacle in this first square, which means that we can't start there. So let's do the obstacle check very first. So if obstacle list, so if the obstacle grid at this y, so y comes first, and x, if this is equal to 1, meaning there's an obstacle there, then we return 0. You can't get to this square. So this should account for all the squares, including the start square. So if we check our obstacle grid first, see if there's a way to even get to this square. If there's not, we return 0. If there is, then we go through the rest of these checks. All right, final thing that we're probably doing wrong. We're not doing any dynamic programming or any caching. That means that we might be calling this same function multiple times with the same inputs, the same x and y. If we do that, then those calls are redundant and we're doing more work than we need to do. So there are a couple different ways we can fix that. The simplest way is to use the @cache decorator, but I'll show you the dynamic programming way to do this. So let's have some DP, and that'll just be a dictionary. Now this dictionary will have a key and a value. The key will be some version of these inputs, and the value will be whatever we return for those inputs. So if we don't have that key in our dictionary, we've never run these inputs before, we actually have to run the function. Before we return, we store that value in our DP. Then we return. If we have seen these same inputs before, then that key will be in our DP, and we can just return the return value without having to do this entire function. So let's do that. So our key, I'm just going to make that a tuple of our x and our y. Now if our key is in our DP, then we can just return the DP at this key. Otherwise, for all these places we have a return, basically we just need to store our value first in our DP and then return. So let's do that. So DP of key here is 0, and then we'll return. All right, DP of key here is 1, 0, 0, and finally down here, well, we're already doing this sum, so let's do this. We'll just store that sum in our DP, and then we can just return the DP at the key. All right, now I think we're done. Let's run this and see how we do. I missed an equal sign. All right, try that again. Okay, this works. Let's submit this and see if we can pass all the tests. And we pass. And hey, it looks like we do all right. We beat 83% for runtime and 7% for memory. That's not bad. Okay, let's jump back here really quick. Let's actually get rid of this DP. Let's say instead of doing the DP ourselves, let's just use caching. So I'm going to undo everything we did with our DP. All right, and now let's just try using the cache decorator, @cache. This will basically do the same thing that our DP was doing. Still works. All right, and we still pass, but we don't do as well as our own DP. So we're beating 33% for runtime and 14% for memory. Interesting. Let's jump back. All right, let's combine these returns here. If x is less than 0 or y is less than 0. All right, that cleans us up just a little bit. Okay, let's do that. Oh, and that makes a huge difference. So now we're at a 95% for runtime and a 7% for memory. So we still have our caching in place, but just by removing one of those conditionals, we make a huge gain in our runtime, 95.2%, 0.02%, and 7% for memory. All right, I think that's probably the best I'm gonna get, but just to show you how we can do this iteratively, let's start over. If you're interested in this. If you're not interested, you're more than welcome to move on, but let's just try this iteratively. Okay, so this is very similar to the way that we did our recursive solution with our dynamic programming. Essentially, when we get to this square, we just need to look up and to the left to determine the value for this particular square. Now, instead of using a recursive function for that, let's actually just start filling in our grid. So we'll create a grid that holds all of our values. That would be the same thing that our caching was doing. And our grid will just start at 0, 0, and we'll move to the right, and we'll move down, and then right and down. We'll keep just traversing through this grid. We'll look up and we'll look to our left to find the value for our current square. And then when we get to the very end, this square will actually hold our return value. So for this one, we actually need to create our sort of working grid. This is where we're going to store all of these answers. Maybe I'll call it answer grid. That'll be better. So our answer grid. Now, that is going to be an array of arrays, so a grid. So the first array will just fill with zeros. And let's see, we'll multiply that by the number of obstacles in our... All right, so I think I'm going to want my max x and max y again. I think, though, I'll use counts instead of finding the index that's the max. I'll use the actual number, the count of our columns and rows. So I'll have an x count. And that's just the length of our obstacle grid at index 0. Very similar to the way we did this before. But instead of subtracting 1, I'm actually keeping this as a count. And our y count, that's just going to be the length of our obstacle grid itself. Okay, so our answer grid, we need to have as many zeros as we have columns for our first row. So that's going to be times our x count. All right, and now I'm going to need one of these for every single row in our grid. So I'll create one for every row. I'm just using underscore here because we don't actually need the value in range, and we'll go from 0 to our y count. So some of you are probably asking, well, wait a second, why did I use a multiplier here, but now I'm using a for loop here? So I can fill this with zeros using this multiplier, but I can't just duplicate all of these by using another multiplier? Well, basically, yeah. So in this case, we're creating a list of zeros. Now, zeros are integers. There's something called an IVAR, but basically zeros are integers. They represent a distinct value. So in that case, I can use this multiplier to just fill this with that unique value. Now, if I were to do the same thing for the entire list and use a multiplier, what that would do is make a reference to that same list. So if I were to fill in our starting space with a 1, so we fill in 0, 0 with a 1, if our rows all point to that same reference row, as soon as I change that 0, 0 to a 1, every single row will get a 1 in its 0 column. So to avoid that, I actually need to create a unique list for every row, and that's what this does. For every row in our range, it'll create a unique list and put it in our grid. Okay, so now that we have our answer grid, we need to kick it off by finding the value for this very first square. So let's do that here. Now this is going to be a little bit different than what we did before, but we do need to find out whether or not there's an obstacle in that first square. So our answer grid at 0, 0, well, let's see, that's going to be 1 if we don't have an obstacle there, otherwise it's a 0. So if there's no obstacle at this very first square, we have one way to get there. We just start there. So that's if our obstacle grid at 0, 0 is equal to 0, meaning there's no obstacle there. Otherwise, it's going to be a 0. There are 0 ways to get to the start square because there's an obstacle on the start square itself. Okay, so now that we have our initial answer grid set up, now we have to go through the entire grid from left to right, top to bottom. So for every x in range, I'll do top to bottom first. For every y in range, we'll go from 0 to our y count. So this is every row. And then for every x in range, x count. All right, so this will take us from top to bottom, left to right. So now we have an xy coordinate, and this is basically the same thing we did with our recursion. First, we'll check to see if there's an obstacle at this space. If there is an obstacle on this coordinate, then we can't do anything and its value remains 0. If there's no obstacle at this coordinate, then we just look at the coordinate above. That's the y minus 1. And we look at the coordinate of the square before, so that's x minus 1. And then we just sum their values. And that's going to be the value for this square. So first, let's check if there's an obstacle. So if the obstacle grid for this, and y comes first, it's always row and then column. So if the obstacle grid at yx is equal to 1, there's an obstacle here. We'll just continue. There's nothing we can do. There's no way to get to this square. Otherwise, let's see, then our answer grid for this x and y. So for answer grid, and actually y comes first, so yx. So we'll just increase the number of ways to get to this square by the number of ways there are to get to the square above. So that's going to be y minus 1 x. And answer grid yx will also be increased by the number of ways there were to get to the square to our left. So that's going to be answer grid at this y and x minus 1. All right. Now, there is one problem I can see here. We're doing y minus 1, x minus 1, but these start at 0. All right, so let's just do a check here. If y is greater than 0, then we'll do this. And if x is greater than 0, then we'll do this one. Now at the very end, we've gone through our entire grid left to right, adding up all the different ways to get to each square. Then we can just return our answer grid for the y count minus 1. We could probably just do -1, -1 here. But let's do it this way. So this is the last square in our grid. I could probably just do -1, -1. We'll try that later. Let's see if this works first. Brackets and not parentheses. Let's see, that should do it. All right, this works. Let's submit this, see how we do. And we pass. And we do all right. This beats 69% for runtime and 97% for memory. So this does a lot better in memory than our other solutions, but not quite as well on a runtime. All right, you can go through and you can probably find ways to optimize this in terms of runtime. There's one interesting thought that I had. I don't have time to go through it right now, but one thought is we don't actually need this entire grid in order to calculate our square. We just need to know the row above and the row to our left. And since we're going through from top to bottom, left to right, we could just keep the previous row and just go through one row at a time, top to bottom, left to right, and ignore all of the rows above our previous row. We don't need it anymore. So basically you just keep one row and move through the entire grid using just one row as your previous row and calculate your current row and then swap them. It's worth a shot. Give it a shot if you have time. All right, that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.